You've probably heard that computers are made up of large numbers of switches. It's true. The 328p processor at the heart of the Arduino has hundreds of thousands of switches. In this video, we'll be looking at some of the simplest ones that can be used to directly control devices. The first thing you might be wondering is, okay, hundreds of thousands of switches. How do programmers cope? That's got to be a nightmare to keep track of. Well, it really isn't. Most of the switches are used as memory. They're very important, but all dealt with in much the same way and easy to understand. Most of the other switches are used internally as part of the chip design and not directly dealt with by the programmer. Finally, we have a few hundred switches that do special things. They tend to be the most interesting, and we'll be looking at some of them here. Programmers don't usually talk about switches. We call them bits. A bit is always in one of two states. Electronically, it has either a high or low voltage. This can mean that a device is on or off, or that something is true or false. Most generally, bits are looked at as being either 1 or 0. Now, a single bit is not all that interesting, and they're usually dealt with in groups of 8, known as a byte. That name was made in fun, but these days everyone's heard of megabytes, gigabytes, and so on. A megabyte really is like 8 million switches. While bits travel in groups of 8, you can still address each bit individually. The usual convention is to refer to bits 0 through 7, going right to left in the byte. Incidentally, you don't hear it much these days, but 4 bits are known as a nibble, half a byte. It must have been a laugh a minute in the early days of computers. Let's get to experimenting with some of the simplest bits on the Arduino, ones that can be used more or less like ordinary light switches. This diagram is from section 5 of the ATmega 328p datasheet. What it's telling us is that most of the pins can be configured to have one of several functions. We're going to use pins 14 to 19 as PB0 to PB5. These are connected to bits 0 to 5 of a byte called port B. There are also bytes called port C and port D, which can connect to the PC and PD pins. In case you're wondering, PB6 and 7 at pins 9 and 10 are not available to us because they're connected to the 16 MHz crystal. Things wouldn't work without that. Similarly, PC6 at pin 1 is dedicated to the reset button, and PD0 and 1, pins 2 and 3, are tied to the serial port that you use to communicate with the PC. Okay, back to port B. The PB0 to 5 pins connect to D8 to D13 on the Arduino, and these correspond with the 6 ThinkerShield LEDs. At long last, let's get to grips with these 6 switches out of the hundreds of thousands in the chip. This is a move instruction, which, not surprisingly, moves a byte in the computer. The details will come later. For now, #0b indicates that a bit pattern is coming next. After the comma is where the pattern is to be stored. Hitting enter, there you go. 6 light switches controlled all at once. Let's try a different pattern. Magic. Some more? You get the idea. You might like to pause and try some of your own patterns and convince yourself that those LEDs are doing just what you're telling them. It couldn't be much simpler, could it? But it is quite a lot of typing. It'd be easier with 6 ordinary switches. Needless to say, the computer can help us with that. So far, you've just typed in the move instructions, and they've taken effect as soon as you hit enter. But we can also store instructions to be performed later. all of that typed in and nothing seems to happen. But it did. The numbers at the start of each line mean that the instruction will be stored in that program slot. So what's this going to do? You already know what those move instructions will do. Wait is pretty obvious, once you know that its units are 10,000ths of a second. So waiting 5,000 is waiting for half a second. You probably guessed that JMP is a jump. Most instructions fall through to the next program slot when they finish. So the move at slot 0 falls through to the wait at slot 1, which falls through to the move at slot 2, and so on. But the jump 0 at slot 4 doesn't fall through. Instead, control jumps to slot 0. Not hard, is it? Let's run the program. How do you do that? The run command. You can give a slot number to start from, but the default is 0, so we just type run. Well, there you go. 2 LEDs light up for half a second, then they go off for half a second, and it'll go on doing that forever. You can stop it by hitting Ctrl-C. There's a very important difference here. To begin with, we were playing with a light switch directly, but now we have programmed a computer to play with the light switch for us. That simple list of instructions stored in 5 slots might not seem impressive, but that's all that computer programs are, on a PC, on an old mainframe, on a supercomputer, or a microcontroller. That'll do for the moment. Next time we'll get deeper into what can be done with bits and bytes. Meanwhile, feel free to tinker. Just retype instructions you want to change. You might try different delays or adding more patterns with extra move and wait instructions. Program slots run from 0 to 255, so there's plenty of room. Remember to complete the loop with a jump instruction. Here's an easy challenge. Rather than a plain blinky, can you make the 3 low LEDs alternate with the 3 high LEDs? Have fun!